Hey, everybody. Thanks for joining us. Welcome to our weekly Wednesday webinar series. So glad you could come on out. Real quick, if you're having any sound quality or video issues, head up to the quick start tab or the audio tab, and then click on sound check. That should resolve a majority of your issues. If that doesn't work, try switching between phone or computer audio. And then finally, if that doesn't work, you can log out and log in and refresh. If you want your continuing educations, watch the entire session, take the survey that pops up at the end. And that same survey is going to be emailed to you right after the session as well. So look out for that. If you don't see it pop up, please just take it once. And even if you don't need CEUs, we all definitely want to get your feedback. Next week, we've got Tim Montague on for pollinator and wildlife-friendly solar farms, the good, the bad, and the bees. Really excited for something like this next Wednesday. And then the following day, we have a virtual citizens participation meeting for the world's first living building in passive house multifamily. It's meant for folks who live in Ann Arbor, Michigan, to get their voices heard since they can't meet in person safely. But anyone can join us from wherever and learn about this project. And then if you want to become a lead Green Raider, we have a Green Raider training on May 11th through the 13th. So check that out. Sign up to become a member, get instant access to all of our webinars, keep these going, support our mission, and get other paid discounts like on that Green Raider training. All right, well, welcome everyone to COVID-19 Characteristics, Transmission, and Control. This course is approved for 1 hour in continuing education units, GBCI, BPI, as well as AIA, Health, Welfare, and Safety, which may make it applicable to your state-based design or contractor license. My name is Brett Little, and I'm the executive director here at the nonprofit, the Green Home Institute, and I will be the moderator of this session today. We're going to be talking a lot about what's going on with COVID-19. It's always a moving target, so I know things will change quickly, and where building science kind of plays a role in that as a high-level concept. And before we get started, a big thanks to our #1 top-tier sponsor for this session, Mitsubishi Electric. Mitsubishi provides all your heating, cooling, and filtration needs all in one. Today's low-load homes require right-sized equipment that most systems, especially gas-fired, cannot meet. Mitsubishi has low-load, high-efficient heat pumps that dehumidify and cool in the summer and work in reverse in the winter. Going ductless reduces costs and can make it easier to meet Energy Star 3 and other green building programs. Ductless mini-splits can now be hidden in many different ways to meet your clients' needs, and ducted systems can be used as well. Ducted systems are hidden behind the walls to ensure a beautiful space and can be retrofitted in place of an existing furnace, single-family or multi-family projects. Hyperheat ensures efficient heat delivery down to -13 degrees, and a backup strip heaters can kick in during the rare but coldest of cold days. Each room of a house can customize comfort while still being all electric and energy efficient for clients with different needs, and only heat and cool rooms that need it. Multifamily and commercial centralized variable refrigerant flow, or VRF systems, work great on larger projects looking to serve whole buildings. VRF heat recovery technology permits for simultaneous cooling and heating, as this illustration depicts. A space can have many purposely designed areas, and each area can require a different heating and cooling need. Check it all out at MitsubishiComfort.com. So with that, I am excited to introduce our speaker and many returning speaker, maybe 4 or 5 times now. Maybe this is the 5th time, I got to go back and count. But it's been several times, and so we're always excited to bring back Ty Newell of Build Equinox. And so with that, Ty, I know I have a lot to go over, so I will hand it off to you and you can take it away.
Great, thank you very much, Brett. And let's see if I can get my screen going here. So Brett said he wanted to put me on camera this time. I don't know if that's for your benefit or detriment, but in any case, I'm here, and let's see if I can get my screen up there. And
there we go.
Super. And I have difficulty walking and chewing gum at the same time, so as you have questions that may come up, Brett, I told him it's perfectly fine to break in and, for clarity or things that are appropriate at a particular time. So I may not notice questions coming in. And if I don't get them during the talk, for sure, whatever time we have left, we'll pick up on. But thank you very much for attending this webinar. And it's kind of odd being in I was going to say the middle, but really at the tip of the iceberg of this COVID-19 disease. And I hope that the information that we discussed, that will be of use to you, both now as well as looking into the future. Just very briefly, and to add my 2 cents on Mitsubishi, our company, Build Equinox, builds a smart ventilation system for residences, what we call the SERV-2, now the 2nd generation unit. And we have a couple of exciting projects in collaboration with Mitsubishi coming up in the next, as soon as things are getting a little bit back to normal, but with Mitsubishi showing the integration of smart air quality maintenance with ducted mini splits. And so we have many years of collaboration with Mitsubishi, and we're pleased to be working with them again. And in our newsletter at Build Equinox, you can read more about these upcoming projects. A deep retrofit, converting a gas heated home over to all electric with 2 1-ton ducted minis and SERV-2 fresh air, along with a simple 1-ton integrated package. Our mission, we're an engineering company. We manufacture the SERV-2, but our mission in life is working on technologies for living in a comfortable, healthy, and sustainable manner. And I think no one said it better than Aldo Leopold. How do we live on a piece of land without spoiling it? So I'm talking to you from a 100% solar powered business, our 4,500 square foot Morton building where we're located and where we build the SERV is a net zero. My house is a 0+ home with 2 electric cars, and you'll find stuff online or in our publications regarding that for more information. Today's topic is COVID-19, the subject of about every news story these days, and we're just getting saturated as well as tough trying to stay isolated. But let me start out by just saying that wearing a mask is not your protection. It's you showing respect and helping to protect others because of the nature of this virus and the asymptomatic nature that we just don't know oftentimes if we're sick, that it's to stop the movement of a cough or a sneeze or respiratory cloud of infectious particles. And we'll discuss that a bit more in this talk, but from reaching others and infecting them. And so I view wearing a mask as a sign of respect as opposed to perhaps an embarrassment that some people may be feeling. We're going to talk a bit about viruses. I'm not a microbiologist. I'm not an epidemiologist. I'm a mechanical engineer, but many, many years of studying buildings and how building ventilation systems should be designed to keep us healthy. And unfortunately, the state of the art in many cases, as we've seen in transportation systems like airlines and cruise ships, as well as commercial buildings and schools and homes, that ventilation systems are often designed to be incubators of disease as opposed to inhibitors of disease. And so we'll talk about that through this as well. But a little bit about a virus, and the characteristics of viral transmission and how to describe it. And then what's very important is this debate about airborne infections. a debate that I don't think needs to be going on, but the CDC and WHO, the World Health Organization, continually tend to downplay the airborne infectious nature of this disease as well as others. But we'll discuss that in light of the past 10 years when very substantial research is indicating we need to be thinking about how we ventilate buildings and how this can both help inhibit as well as designs that prevent incubation of disease. And then finally, we're going to talk more directly about COVID-19, the brief history of it over the past couple of months, where we are today and where we could be going, and some of the ways we can think about controlling this, as well as with recent technology, how we can, say in real time, track how well we're doing in getting it under control. To put things in perspective, as many of you probably have a lot of interest in buildings and especially in energy. And my background for sure is in energy conservation, energy conversion, renewable energy collection and storage. But I think of energy as secondary or as a constitutive relation. It's a constraint. It's not the objective. You don't build a house in order to conserve energy. You build a house to keep yourself healthy and comfortable. Similarly, a refrigerator is not for saving energy. A refrigerator is for preserving food and keeping you healthy. And I think we sometimes lose that perspective that as you think about designing a house, think about it for 5 generations or more of people who will live in it, and the things you might be able to do to prepare for others rather than just your own personal preferences. And in terms of costs, as we move toward sustainable residences and think about how much it's going to cost as far as supplying the energy to that home to keep us at a higher quality of level of living that we currently enjoy today. That is, we don't backslide in quality and comfort, we advance it, we make our homes healthier. But the energy we will need in homes like the house I live in, and many of the homes we're seeing in projects, wonderful projects that many of you are involved in all around North America as well as the world, these homes on average will cost in the US about $160 billion per year, with about half that for people, TVs, cooking, hot water, things of that nature, and about 80 billion for climate, and then plus or minus 20% depending on what climate zone you're actually in. But climate just becomes a less substantial driver of energy costs. And that's based on a simple metric, but one that we've done a lot of field studies as far as actual energy usage in high performance homes and regular homes. And this is a very realistic number. It's not taken out of or derived from a number of other studies. About 4,000 kilowatt hours per person is the energy that we basically need throughout the US and much of North America. And when we compare that refrigerator energy in a similar manner, about $5 billion a year of that 80 billion for things people like to do in their homes. When we compare that to the costs of other things such as food or our health, the purpose of a refrigerator is food preservation. It's not saving energy. And if you're finding you're spending an inordinate amount of time looking at a refrigerator that might use 350 kilowatt hours a year versus 400, instead of looking to see whether or not it's got a nice design for produce preservation, for other food storage, that it has good reviews as far as its durability. This is where the value comes in on the refrigerator. We put about $2,000 worth of food per home occupant in a refrigerator each year. and that's about $600 billion worth of food. And unfortunately, we lose about 20 to 25% of that food. And that simple calculation shows you that's equivalent to the entire energy cost for homes that I projected above. And add on top of that, foodborne illness is estimated in the 50 to $70 billion per year. So all of a sudden, this food issue is a much bigger problem within our homes than energy. And it's a low-hanging fruit. We can design refrigerators better that preserve food longer, that perhaps sense when food's gone bad so we don't ingest it and become sick. The purpose of a refrigerator is keeping food healthy and storing it for periods of time for us. The same as your house is to keep you healthy and comfortable and secure. Those are the objectives, with energy being one of the constraints to help us get there. Now, when we talk about a normal year of influenza and colds, the cost is about $130 billion a year, roughly broken up between flu and colds, as I've shown. And one of the studies that I'll cite, a very substantial study by Dr. Donald Milton, University of Maryland, that buildings, commercial buildings that have higher rates of ventilation, 50 cubic feet per minute, rather than the rule of thumb, say 20 cubic feet per minute. But in his study, the difference between 25 and 50 CFM was a reduction of sick days of employees of 40%. And that's equivalent to the effectiveness of flu vaccines. So just think of it, this very simple change of ventilation rate, and it's got a very modest cost. Other studies have shown without any energy, any additional steps taken for energy conservation with this increase in ventilation, that it roughly equates in the workplace to about $50 per employee per year, in comparison to several $100s for sick day reduction. And then the big dog further down on cognition productivity, this ventilation has the additional benefit of about a 10% employee productivity increase, a 10 to 15%, and that's roughly about $6,500 per person. It's a difficult thing to meter, of course, but even if it's off by a factor of 10, you're trading $50 for improved ventilation for about $650 of employee productivity, as well as reducing sick days by about another $500 or $600. And just another example, asthma is about $60 billion a year. We've more than doubled the number of folks in the US populace, but around the world as well, afflicted by asthma. And this health cost, if we could get it back down below 5% by improved ventilation, by using materials that we haven't been immersed in the chemicals that they've been emitting, that perhaps here's another 25 billion or more that we might save. So energy is important, but there's many other things that need to be upfront in consideration when designing a home. And now this black swan of SARS-CoV-2, the virus causing COVID-19 illness. This is in the US greater than a 4 trillion and counting problem. So we need to think beyond energy.
Ty, one of the questions that came in was, how is cognition productivity degradation measured? I believe was how it is. Yep.
Yeah, just briefly, and you'll find in some of our writings, and then a work that I'll cite in here, but studies by Harvard University, Harvard School of Public Health, along with SUNY New York, and Carrier Corporation were all involved. And Lawrence Berkeley National Lab has been involved in these studies, that at carbon dioxide levels that we had traditionally thought of as being benign, roughly about 1,000 to 1,200 parts per million, which is a level that you get with about 20 cubic feet per minute of ventilation airflow, that we actually suffer about a 10 to 15% degradation in cognition productivity. And the test that studied that from the SUNY, the State University of New York Medical Campus, is one that's been vetted on thousands of people, in which they study about 9 different areas of cognition, from creativity to decision making to organization of information and things like that. And they showed, but it's not understood why, that as you increase CO2 from about, say, 800 parts per million above 1,000, that there's this gradual decline of cognition productivity. And so this metric and the value placed on it is based on that. And on our website, you'll see a paper from the Harvard School of Public Health describing that study, as well as a follow-on study where they did a simulation of the workplace to look at the cost of increasing ventilation airflow without added energy conservation measures in different climate zones throughout the country, and came up with that cost-benefit ratio of $6,500 of estimated employee productivity relative to, in challenging climates, about $50 per employee additional ventilation costs. So that's the background on it, and you'll see other webinars like we've done with the Green Home Institute describing that in more detail. Last fall, before all hell broke loose, I had the opportunity to visit the Florence Nightingale Museum in London. And it just happened to have a special exhibit on the Spanish flu, and very graphic, very wonderful exhibit showing the origin, the rapid propagation of it. While it's named Spanish flu, it's suspected that it may actually have originated in the US, possibly in Fort Riley, Kansas. And with our troops moved over to Europe for World War I, spread throughout Europe, but nobody spoke about the flu, as everybody was keeping quiet about difficulties, the British Army, the French, the German Army. And as it spilled into Spain, which was neutral, Spain started calling attention to it, and so they got branded with the moniker of it. Its actual origin is not known, but it spread like wildfire around the world with 3 waves of infection. An initial spring wave, as we're seeing with COVID-19, a reduction in the summer, and then a large wave that was the main wave killing and infecting people throughout the world in the fall, and then followed by another smaller spring wave. It was disastrous. Communities that did not isolate effectively, like Philadelphia, had tremendous losses, where others like St. Louis were better prepared as they saw the wave spread through the country. This, and Florence Nightingale is just a brilliant person. I have a couple of sayings from her, but her book, Notes on Nursing, is today a wonderful read, very well written and very apropos to things we need to consider in designing buildings. My great-great-grandfather, John Newell, and you can see my forehead is rapidly approaching his, along with my beard maybe catching up to his during this period of hibernation. He was a mayor of Port Huron in Michigan in the 1860s and public health officer in the 1880s during a smallpox outbreak. And reading a public record he had written on a smallpox outbreak, similar to today, people didn't want to be quarantined. They had to force people to stay in their homes that had contact with smallpox. It is such a deadly disease, blinding about 1/3 of infected people. And he also described that doctors in town refused to go to the homes where he found people that had been in contact with infected persons, and that the cost of vaccines, because a vaccine was available, although it was a fairly dangerous vaccine, that people were selling it for 50 cents to $1, a tremendous amount for an inoculation at that time. And so many of the same things going on then as today, but something that they absolutely knew as a knee-jerk reaction. As soon as you saw an infection of that type, you isolated and quarantined, you tracked down who had been in contact, and you quarantined them. That's how you snuff out a disease. ASHRAE, which I'm a member of, not a member of this committee, but this statement, which is a little too detailed to read, but basically says that ASHRAE feels it is very, very likely that air conditioning and ventilation and airborne exposure of the virus needs to be controlled. And basically what they're saying is you need to enhance your ventilation, your fresh air ventilation, not reduce it. That the way to isolate is not mean turn down your ventilation, increase fresh air, increase filtration. A MERV 11 and greater is needed to be pulling out viral particles. We'll discuss that. And you need to stay comfortable. That people who are sick, comfort is a big part of being healed. So avoid thermal stress. And Florence has things to say about that. It's just important that fresh air is going throughout a home and that there's no area in the home that's left stagnant, which unfortunately is not the case in many of our homes and buildings these days. Just a little bit on viruses, that a virus, there's a debate, is it living or not, but it's really a cellular parasite. And it's also important to know that not all viruses are bad, that these are parts of the toolkit being used today to help manipulate for beneficial manners different other organisms. But these viral particles, when you ingest enough of them, that they find a host cell, they replicate, they're very tiny relative to the size of a bacteria or size of a cell in the human body. And in various manners, as they attach to a human cell, and respiratory viruses tending to be in the respiratory tract and in the lungs, that they then are able to put their genetic material inside the cell, hijack the replication machinery, the DNA within a cell, and start spitting out pieces of new viral particles. And at some point in time, they're released from a cell in various manners. And so there's various families of viruses, and the COVID-19, the SARS-CoV-2 virus, is part of what we call respiratory viruses. I have a number of references at the end of this that these numbers refer to. So this number 2 is a very current review of respiratory viruses. It's an excellent paper that I recommend, very current, but it's also very deep as far as covering a range of viruses. And among respiratory viruses, there's some that are classified as winter peaking viruses, such as influenza, the human coronavirus, which the SARS-CoV-2 is a member of, and the RSV virus, which causes a cold-like illness. These tend to peak in the winter, while other viruses tend to peak at other times. For reasons not understood, and excuse me just a sec. Sorry, I thought I had that off, and I didn't. For reasons not understood, it also seems like there's an interplay among viruses. So as COVID-19 has spread, there's been a noted drop in influenza. What that interplay is among viruses, one peaking versus another, and how they figure that out, we don't know. But these winter peaking viruses, it's not understood why they're more readily adapted, say, to winter season. But as we've seen viral spread in places like Louisiana and Singapore and elsewhere. We know that they are viable in warmer and more humid places, but they do seem to favor cooler, lower humidity level environments. In addition, human physiology in cold weather, the mucus layer in your respiratory tract is thinner, and this is a protective layer between the cells lining your respiratory system, as well as the ciliary movement, the hair-like structures on those cells that move mucus up and through your throat to be expelled or swallowed. And these are also thought to be a reason why these viruses may be more viable or potent in winter conditions. And then wintertime, shorter days, less sunlight, that less vitamin D production, our immune response drops too. So the confluence of any of these things and our behavior, are we in more contact in the winter, sealed up with lower ventilation, less fresh air in the winter? But a mix of these factors may be the reason why they favor that time of year. A parameter called R0 or R0, the basic reproduction factor, is an estimate of for different infectious agents, their spread among a general populace that's all susceptible. So an R0 of say 2 indicates that you take one infected person, put them in a populace that's all susceptible, and during the time that they're infected, they would be expected to infect 2 other people. And the basic idea of R0 is that when it reaches 1, the spread of that disease is no longer viable. It dies out. And in this list, you see that the ranges aren't fixed. It's not a universal constant. It's a characteristic of a populace and how they intermix and mingle, as well as seasonal factors, as we discussed. So for COVID-19, a best guess right now is that it has a R0 greater than 1, so it's going to spread. And the plot over on the right shows the fraction of the populace, if everyone's susceptible and if there's no vaccine available, that with an R0, say in the range of 2 to 3, and letting it run rampant without isolating, without testing and tracking, that 50 to 70% of the US population, or 160 million, 225 million, would become infected. And with a 1% mortality, although, as you're seeing, different age groups, different countries, different regions are experiencing wildly different levels of mortality. But we would expect a horrendous 1 to 2 million fatalities from this disease. The goal with isolation is to try to move the effective R0 down as close to 1 as possible, so that enough people can recover and are no longer infectious, that then we can get to a system where we can reliably test, track, and isolate. And we'll talk about that more as we go on. You can see these other diseases. Measles, without a vaccine, it would run rampant and basically everybody would get measles. With a vaccine at about 95% coverage level, this critical vaccination limit shows what provides a herd immunity due to a vaccine. And with COVID-19, we need somewhere in the range of maybe 60% or so if we get an effective vaccine in order to provide that herd immunity, rather than trying to do that through letting everyone become infected. Some countries are going the herd immunity route through infection, like Sweden. I think there's too many unknowns for that to be a good gamble, but they're running that experiment, and we'll see.
Hey, Ty, can you quickly elaborate why you've got 2 different ROs for almost everything here?
So this is just kind of a best estimate of the range. So, it's not a fixed number that's defined real well. So let's say maybe a region that is a little more humid and warmer, maybe the R0 of that populous group, or just the way people's behavior is, how they interact with each other, that in some regions of the world, the R naught is maybe on the lower end, like 1.4, where other areas where maybe a more metropolitan area or just people are in closer contact, poor ventilation and things, that it's got a higher reproduction number. So it's a fuzzy number, and we'll talk about a building R naught in a bit. So once you get inside a building, this factor changes even more, but it's really a measure of the replication of a disease, starting with one infected person going into a populous group. MERS, Middle East Respiratory Syndrome, which is very similar to the SARS viruses, the same family of coronaviruses, you can see that that seems to be a self-extinguishing disease that doesn't propagate. It's an extremely deadly disease. I think about 30% mortality. And so it's critical anytime this rears its head to get on it, since it is something that is very, very difficult to treat. But again, this R0 tends to indicate within the way a general populace interacts, it would not propagate, it would self-extinguish. But that's not true as you get into a certain building, a certain type of ventilation, a certain type of local environment or populous behavior. That can go above one and then infect a number of folks. And smallpox, you can see, as my forefather had to deal with, this thing would just take off. I mean, even more spreadable than 1918 flu and COVID-19. And so they were managing, and smallpox is now considered eradicated because of very strict tracking and isolating and quarantining. And that brings up with COVID-19, perhaps not the easiest way and very difficult to do in a practical manner, but if we were each put in an isolation bubble for 3 weeks, so those of us who are infected, whether we know it or not, and those of us who are not infected, it would snuff itself out. It would run its course, good or bad, within those infected folks, and then it would no longer be prevalent. It would be extinguished. But of course, we can't fully shut down. So CDC says, and the World Health Organization, that it's primarily by large droplets that fall within 6 feet. And as we'll talk about, that ain't true. Don't touch your face, that's true. Wash your hands, that's true. But 6 feet, it's wishful thinking. And also that it's by fomites. These are objects that, say, you cough or sneeze on that are covered with infectious droplets that then you touch, and then you touch your face or your mouth, or you breathe infectious particles off of those objects. It's not just droplets putting this layer of viral particles on objects like your cell phone, a remote control, a tabletop. The airborne, or what's called aerosol transmission, is significant in determining it, and the ventilation level that is operated is critical for reducing the concentration of airborne contagion and its ability to layer and coat objects around an infected person. So we'll talk about some current research. So I'm not sure why the precaution guidelines are like that, but in their view, this homogeneous aerosol spread of droplets that are, say, less than 5 microns that are floating in the air as they radially disperse from who's ever emitting them through a cough, a sneeze, or just respiration and talking, that it no longer has a concentration level that can infect someone. But if you think about that aerosol concentration, just like a carbon dioxide concentration, the greater that concentration and the lower the ventilation rate, the greater that airborne concentration will be. And at some point in time, it does impinge and or gets attracted to other surfaces and layers out, that this is a primary avenue of coating things with infectious particles. Particles that are greater than 5 microns are considered a drop, but as we'll discuss in a minute as well. A 10 micron particle takes its time to drop, and somebody walking by is more than enough to drag that particle along with them rather than gravitationally falling to the ground within 6 feet of someone. So I just think that this is not a very practical viewpoint. Just some evidence, and you can download this from our website if you don't have library access, but I feel this is one of the most important papers demonstrating on a large scale, as I mentioned, increasing ventilation from 25 CFM per person to 50. That this study by Professor Milton and colleagues, he's now at University of Maryland, but was at Harvard at this time, that he found that it was as effective as the flu vaccine, reducing sick days by 40%. So there's an economic advantage to doing this. And basically this means that in your buildings, whether at home or at work, you should seek to keep carbon dioxide less than 800 parts per million. So if you have one of these simple carbon dioxide monitors, check and see where it is, and if it's getting up above 800, increase the ventilation rate, open windows, increase the fan speed. Your health, your cognition productivity will thank you for it. So on a recent research basis, airborne transmission exists. There's no ifs, ands, buts about it. Professor Lowen's study that I reference here, but other models as well, where she takes a number of guinea pigs in cages, some that are infected with flu virus, others that aren't. The cages are spread apart so that there's no chance of direct contact, but simply the circulation of air around in the test chamber. And she's shown very effectively also for respiratory illnesses that are winter peaking that there is definitely a sensitivity to the humidity level as well as some to temperature level on the viability of the virus. As far as droplet experiments, Professor Marr at Virginia Tech and colleagues, and then several others as well, but over the past 10 years, as we're able to track much smaller droplet sizes, much less than say 2.5 microns, and a human hair is about 100 micron diameter. So these are very tiny. Even a big droplet of 10 micron is not that big. But she has found that when she uses mucus, when she has viral particles suspended within real human mucus, that the viral particles live longer outside the human body than when put in, say, a saline solution to simulate droplets. She also, in this reference, shows that a 10 micron drop takes 9 minutes to fall 5 feet. That's about 30 feet per minute. Your walk, a leisurely walk, is 100 feet per minute, about the typical air current ventilation flow rate within a room, 100 feet per minute. That's going to drag 10 micron big droplets around a room. No ifs, ands, buts about it. So just thinking that it's going to drop leisurely within 6 feet of where it's been released is just fantasy. And then even smaller droplets take much longer time, so much so that they're essentially suspended, just floating around within a room. And the ventilation rate will determine the concentration level of those viral particles in those small droplets. And Professor Marr also showed, as well as other researchers, that within a second of being expelled from the human, that droplets over these size ranges reduce to about a third of that diameter through evaporation. Very quick evaporation process on these very tiny particles. So that even though the bulk of the mass coming out of somebody coughing, sneezing, breathing may be larger than 10 microns, and that may be where most of the viral mass is located, these quickly drop down to a original 10 micron droplet becomes 3 microns within a second and becomes an airborne particle. And then much larger particles, 20 to 30 microns, becomes a 10 micron particle that's leisurely falling. It's not like a rock falling with gravity. Professor Buriba out of MIT recently wrote this article, but she studied this for several years, that when you cough or sneeze, a cloud comes out. And just like clouds shouldn't exist in the sky because they're non-equilibrium, how are these droplets going over our heads each day, that this cough sneeze cloud, it stays as a coherent fluid mechanics structure that moves 20 to 30 feet. It's somewhat buoyant, so it stays about head level from the person who sneezes and coughs. And so it's a very concentrated mass of viral particles. And then, of course, the ventilation flow of air through a building is very complex, and it can grab this cloud of viral particles and move it in any direction, as well as somebody walking through it. So as you're walking down the aisle at Walmart, 20, 30 feet away, that viral cloud from somebody at the end of the aisle may be breezing past your head. So you want to be aware of it, and that 6 foot spread is not a safe factor. Use your head, stay clear of people when you have the choice. And finally, Professor Brent Stevens at Illinois Institute of Technology, who studied biomes and residences for several years. But he took a test size residence, kitchen, living room, bedroom, with a typical ventilation system, and he released bacteria, and then he did other tests where he released viral particles with a kind of a cough breathing machine that replicated the way a human respirates particles into a space. And he found that the viral particles were spread throughout the space. He also found that, and bacterial as well, although the interesting thing with the bacterial is that because a bacteria is a similar size to these droplets, it often was ripped apart. And even though that may seem like a good thing when a bacteria is ripped apart, several bacteria in the category called gram-negative bacteria, when they die, the shell of that bacteria produces something called an endotoxin or an LPS molecule. And these are very, very toxic. And while it's unknown, it's been speculated it also acts as an adjuvant that in something like, say, an asthma attack or a virus attack, that this may actually enhance or amplify the attack of that infectious agent. He also showed that MERV-8 filters do not remove viral particles, but MERV-11 and MERV-16 successively remove viral particles, and we would recommend using at least a MERV-11. Our ventilation systems are sent out with MERV-13. And coincidentally, a friend yesterday called me up to ask me about filters because he had called his HVAC installer for the new home that he lives in about what filters they would recommend. And they said, oh, definitely not anything above MERV-8 because they clog up too quickly. And I told him, well, that's kind of the point of a MERV-11 and MERV-13 is you want it to clog up and catch those particles. And so don't rely on your local professionals if that's the type of advice you're giving. You want to filter out both those particles as well as particulates in general.
Ty, is it fair to say that their concern is trying to slap those bigger filters into existing furnaces and cause potential harm or damage. I mean, would that be a fair thing to give to
Yeah,
them?
I think that, yeah, they're going to get less airflow if their system hasn't been designed properly, adding that additional pressure drop. Although if they have enough filter face area, it should not be a noticeable pressure drop. And filters, as in various studies have shown, they actually become better filters with time because of the clogging. But typically with a MERV 13, from our experience, that you should get a good 3 months out of that, maybe a little less in a dustier part of the year, the summer or a very pollen generating time of year, and maybe more in the winter time as things are dampened down and not quite so dusty. But there's some very good filter studies that are showing that you need something in that level to remove viral particles, as well as to get these 2.5 micron particles out. And a MERV 8 isn't going to get 2.5 micron particles out. The particles that you ingest deep into your lungs and that cause problems in various manners beyond viral infections, things that look relevant or correlate with stroke, heart attack, Alzheimer's, and things of this nature. There, more recent research, by recent, not just years, papers are coming out right and left every day now. These tend to be going into peer-reviewed journals, but as preprints without the peer review process is currently going on. So for example, this reference from a number of co-workers looking at the longevity of SARS-CoV-2 virus in aerosols and on different materials, seeing that it's viable for 3 hours in air. That means that there's more than enough time for it to circulate, for it then to land on a surface or impact the surface and cover it in time, and then perhaps live even longer from that point. And with somebody shedding virus for a 2-week period of time, they can really be coating whatever space they're inhabiting with these infectious particles. Copper, which has kind of a germicidal, a biocidal nature to it, the virus seems to only last about 4 hours, where cardboard, and the interest in cardboard this day and age of shipping things from here to there, is about 24 hours, while stainless steel, a fairly inert metal, as well as plastics, the virus seems to stay viable for up to 2 to 3 days. Another recent paper, as far as airborne transmission, this, which I think is publicly available, but if you look up this Guangzhou restaurant infection paper, it's also a preprint, but it very definitely shows how these look like 2 ductless mini splits, although they don't define the air conditioning system. But one half of the restaurant had one air conditioner head blowing air and recirculating it around customers in that section. Adjacent to that section was a side that had one person who was infected, and with the testing and tracking going on in China, they were able to do the testing and linking of that infectious person and subsequent infections. And within that restaurant, within this area where a second air conditioning head was recirculating air, that 9 other people became infected. And they were sitting at different tables. They were not part of the group at this table, although some additional people within this family group were also infected. But it very definitely suggests airborne infection is an important path. And then University of Nebraska Medical Center, which is one of the top isolation centers for contagious diseases. They studied the rooms, the isolation rooms that had SARS-CoV-2 patients in them, and they were wiping surfaces and objects within the rooms, looking for where viable viral material may be setting. They found genetic material on everything in these isolation rooms. About 2 to 3 copies of genetic material, and this should be per microliter as opposed as opposed to milliliter of material wiped from cell phones, toilet seats, dressers, and even under the bed. It was a similar concentration, which is telling you the air recirculation within the room is evenly layering this from aerosols and larger droplets entrained in the air throughout the room. One would think a cell phone and a remote control or a hairbrush handle would have much higher levels of viral genetic copies, but they don't. Under the bed is about the same level. The highest concentration was on the ventilation return grate, suggesting that a lot more viral copies were heading through that grate for filtration before exhaust. These rooms are 100% fresh air. They're very high levels, 15 air changes per hour. So compared to the 1 or so or less air change per hour in most buildings. And the air itself had the highest viral loadings, about 8 genetic copies per liter of air, a bit different measure. They also found, even though this has a negative pressure ventilation system so that the hallway going into an antechamber heading into the room would have a net flow from the hallway into the antechamber into the isolation room, they found viral contamination in the hallway, suggesting that the virus had landed on the medical staff as well as was entrained with them as they walked through the antechamber and back into the hallway. And that research is continuing on. And then a recent paper by some physicists at New York University just looking at how structures like a sneeze cloud can be transported in odd pathways throughout any room based on the way the ventilation system flows through the room. So the actual situation is much more complex, that there are these complex flow structures of viral particles moving through a room just on their own, as well as entrained, and that the concentration of this airborne aerosol is very much dependent on the ventilation airflow rate. And as I suggested, keeping the CO2 concentration below at 800 parts per million or less to reduce that concentration based on Dr. Milton's work with general influenza and cold transmission seems to be a level that helps reduce that mode of disease spread. So just talking some about ventilation then, that it can either be an incubator of disease, as we often see in transportation systems like trains, buses, airplanes, and as much as these airline CEOs are telling us that they're circulating the airflow through an aircraft, they're not always doing that. It's not reliably kept ventilated, and I'll show you some data of that. I wanted to talk about how CO2 is related to the spread of disease. Again, Dr. Milton with another colleague, Professor Rudnick, when they were at Harvard, that they linked ventilation rates and CO2 to the spread of airborne disease, respiratory viruses, and it's through a model called the Wells-Riley, which is a well-known model for airborne disease or respiratory disease spread. And I won't go in the basis of that, but if you look up Wells-Riley, you'll see a history for that. But basically, an infectious amount called a quanta, which describes the probability that you're going to get sick. And when you ingest 1 quanta of infectious material, and that doesn't necessarily mean 10 viral particles or 20, it's very disease dependent. But a quanta is a probability that you're going to become infected. And 1 quanta means that roughly 60 to 70% chance of being infected. Well, with that model, if you put 10 people in a room, one's infected and 9 are susceptible, based on the CO2 level in the room, the higher the CO2 level, the higher your probability of getting infected. And rather than just purely thinking of it being the airborne concentration of it, also think in terms of that higher concentration of infectious materials in the airborne aerosols, that this is layering coating on your cell phone, under your bed, on the toilet seat, elsewhere throughout a room. So rather than just thinking of it as something you're breathing in, it's getting layered. And the higher its concentration, the higher the fraction of air that you're breathing that came from someone else's lungs that was infected, the higher your probability of getting sick. And so that's how carbon dioxide, it's really a surrogate or a tracer for indicating on the right-hand scale the fraction of air you're breathing that was already breathed by somebody else in that room. And on the left-hand side, if relative to ASHRAE level of ventilation, around 20 CFM, that red line indicates the probability that you'll get sick if you're in the room for an hour exposure, 4 hours or 8 hours. And if you move that down to 800 parts per million, that probability is decreased. Now, coupled with that probability is this reproduction number, but instead of the basic that I showed in that table, a building level, which is to say, based on that one person going in that room with 9 others, how many others are likely to get infected? And this reproduction number indicates that if you're only in that room for an hour, and along the red line, that's the 20 cubic feet per minute time period, that you would expect 1.5 people to become infected. If you're in the room for 4 hours, you'd expect maybe up to 5 people. And if you're in the room for 8 hours, 7 people. And if the concentration were, say, 2,000 to 3,000 parts per million, you're going to be in there long enough to infect everybody. Likewise, moving down to 800 parts per million, and if you're only in the room for an hour, you can see that this building reproduction number is getting down to 1, the level at which the spread of the disease will die out. And so the reproduction number is also within that local environment impacted by that ventilation rate. Now, let's say you go to a gathering of 100 people for whatever, a theater, political rally or whatever. It seems kind of contradictory that your probability of getting sick, if there's only 1 infected person and 99 that are susceptible, that now you see at, say, 1,000 parts per million with 20 CFM per person ventilation, the chances you're going to get infected by that one person, because the fraction of that carbon dioxide that came from other people's lungs, that now your chance of breathing in an infectious dosage from the sick person has been reduced by a factor of 10. So that seems like, well, maybe gathering isn't so bad because my probability of getting sick is reduced relative to that room with 9 other people or a room with just 1 other that's infected person. When we look at the reproduction number, though, it tells a different story. That person released in that room of 99 people, instead of possibly making 1 person ill or 5 persons or 7 persons, we see that if we're in that room for an 8-hour time period, maybe 15 people are going to get sick. Or we don't have an effective ventilation system and we're getting 2,000 parts per million and we're in that workspace for 8 hours, that now 30 people are going to get infected. So large gatherings are just a very, very bad factor when disease is running rampant like this. As we look at different spaces, and we'll just briefly consider this, but on the right is showing the carbon dioxide on a flight that I took a couple years ago from Philly to Burlington. Airline CEOs are saying they have 20 air changes per hour on aircraft. No, that ain't so. Here's 1,550. I caught the flu after this flight. It's up to the pilot. They need to have CO2 sensors on these aircraft, and they need to monitor them and keep the CO2 levels below 800. Very dynamic, depends on the number of people on that flight, but more often than not, you're going to find unhealthy levels of CO2, as well as sneeze clouds and cough clouds floating past you within the aircraft. They need to do a better job, as well as other transportation systems. There's a couple of things just as far as suggestions for low density occupation like a house, 1,000 square feet per occupant, typical. Use MERV 11 filters. Continuous recirculation in order to get viral particles out is extremely important, and a lot of homes don't have continuous recirculation of any type, building up concentrations in rooms. And then with complex rooms, zone control and distributed sensing may be in order. When you get to medium density, like a workplace or a school, maybe 100 square feet per person. The design in which the entire building is connected by a large ductwork, usually dictated by comfort conditioning, is just bad. We hope people start gravitating toward local fresh air design for each office, classroom, meeting room. And we're seeing that happen. But why should somebody on that side of the building make other people on this other side of the building sick? And there's ways you can do that that save capital costs too. As far as high density occupation like transportation systems, these are very dynamic spaces, and they need to have the controls, the smart ventilation, in order to bring fresh air in as it has high occupancy, and then times when it doesn't need so much with low occupancy. This simulation of a house, what's typical of the average US home now, 2,700 square foot home with 4 bedrooms, and ASHRAE anticipates 5 occupants, that home would have, with an occupancy schedule as shown here, it would have maybe no one in the home from 8 to 4 during the day, people back at home and active from 4 to 10, asleep, so at home but less active, but in the bedrooms during that time, and then waking up and active before leaving in the morning. And they would be in bedrooms or in the main room. So this simulation, on average, if the house is perfectly mixed under ASHRAE ventilation standard, it's keeping a level of concentration that looks not that bad. And but when you look at each of the individual rooms from this computer simulation, you can see here this bedroom, the master bedroom, and the individual bedrooms don't look so bad, but the family room gets way out of whack as people gather there. Well, maybe out of this 120 CFM, you squeeze more airflow into the main room and less into the bedrooms, but now this is going to go up. And if you happen to have one person sick in a bedroom, again with ASHRAE 62.2 scheduled ventilation for this house, the concentration of CO2 for this continuously occupied bedroom at 10 CFM is extremely high. And if you're the caretaker walking into that room, you want a mask. You want to be in that room and out of that room. Keep that person isolated as much as possible. And if you do have someone sick in a home that you're a caretaker for, open the windows. Open the windows in that room, as Florence Nightingale said, as much as you can without chilling them, and get fresh air in, dilute the contagion, Do not allow it to spread or to land and coat things. Um, uh, Here's some real data, just so that simulation data, I know there's a lot of you that want real data, and rightfully so. Here's an 1,800 square foot ranch home. It's a radiantly heated home, so it has no active ventilation. It's a leaky home, 1950s construction, and no renovation to seal it up. So this myth about leaky homes having fresh air, it's purely a myth. More than half the leaky homes that we monitor, we find bad air quality. Where the leaks occur and where you live are two different things. So bedrooms are notoriously polluted, leading to poor quality sleep as well as infectious spread. This is a bedroom that two small children share. When their parents put them in the bedroom, it quickly soars up in CO2. And when they finally fall asleep by about 9, the parents open the bedroom door, which then somewhat levels off the CO2, but at extremely high levels. That basically means within this family of 5, when anyone gets sick, and you can see in the main rooms as well, the CO2 level regularly getting up to very high levels, that everybody gets sick. So here's a smart ventilated home. This is actually my home, and you can see data for Equinox House on our website for the last 4 or 5 years or so, as well as what our current control settings are for it. It's all online, and you just have to click on the controller on the front page, the home page of our website. But this yellow line is the CO2, and there's also a VOC sensor in the serve. And I typically keep it at 850 parts per million. But if you look at the current control settings, you see that I have the serve set at 650 parts per million. And whenever this yellow line hits that threshold, it then goes into fresh air mode and drops the CO2 down to 750, 100 parts per million below the upper threshold. And then as it moves around, here it hit the threshold again and again went in fresh air mode. This bulk air returned to the serve is managing the air quality in the house. These other lines are separate CO2 monitors placed in the master bedroom, an unoccupied small bedroom, and then the main room. And you can see that there is a difference in CO2, but in general, not the wild variation. So here's, say, the worst case over this couple-day period, where the master bedroom got up near 1,000 parts per million. But in general, because the serve is always recirculating air when it's not bringing in fresh air, and it's always filtering out particulates, and that's an important aspect of the filtration, but it's evening out the level of contagion within the house.
Hey,
Now, yeah.
I'm wondering, we're coming up on our time, and we've got a lot of amazing questions here.
Okay.
I'm wondering if we can just quick do the little outro, and then if we can start answering some of those questions, and maybe you can use some of your slides.
Let's do that.
Is that fair?
Yeah, let me end on a couple of slides here that just to state where we are now. This slide shows US COVID infections relative to other countries. And you can see that the US, while we've stopped the exponential growth, we have this uncontrolled linear growth still, while others are tending to bend this over and their recoveries are outpacing their infections. And I just want to mention this infection parameter that is similar to the R0, but I use it for simulating the contagion. And this parameter over a 14-day period basically describes when how many people one infectious person may have infected. And you can see how the US soared in March as the infections took hold. And then as we started to isolate, we were able to get this down relative to other countries. And South Korea is definitely the model, and then the state of Washington as well within the US, for testing, tracking, and isolating. But when that doesn't happen, you end up shutting your economy down. And lastly, I just want to point out that this infection parameter, that we were making great progress getting down below 2.5 and 2, but now we started backsliding over the past week where we haven't made progress, and now the infection parameter is looking like it's rebounding up to about 3. Not the level that we had that was skyrocketing, but this prediction through May, so this is as of about a day ago, these are the total infections. If we can keep that infection parameter, effectively isolate ourselves through the month of May, we may be able to, with recoveries, get down to only 200,000 infections. If we had done better in April, getting infection parameter down below 2, as many other countries are doing, this number would be down around 10,000. But because we haven't done it, I expect this to be around 2,000 to 500,000 active infections by the end of May. And if we backslide and don't isolate and get up to what's still a fairly modest infection parameter of 7, we'll see 400. And because this is a path that gets preordained by things that happened a week ago or 2 weeks ago, it's very hard to change this course if we start heading up here to get it back down again. So I just want to mention that. And this last slide, the University of Maryland has done some very interesting things, and others are as well, with GPS tracking of cell phones, anonymous GPS tracking of cell phones and vehicles, and then formulating that into what they call a social distance parameter. 100% social distance means total isolation, and where the US normally is around 20, but I've been able to plot this infection parameter, this number of infections per infected person parameter versus their social distance parameter, and you can see it correlates quite well. And if we backslide as we're doing, we will start to see the infection parameter start to multiply. And if we happen to backslide and are unaware that this virus is likely to become much, much more efficient in transmitting in September and October, perhaps like the Spanish flu, we'll be in real trouble then. Right now it won't seem so bad. So I want to thank everybody, and sorry for running over time. Let's get to some questions for those that are remaining, and anyone else, please for sure feel free to contact me at any time.
Yeah, thanks, Ty. And we do got some great questions coming in. Real quick, make sure that you take that survey that pops up, or the same one will be sent to you in your email. Just take that to get your CEUs, or even if you don't need CEUs, we certainly love your feedback. If you're watching this in the future on demand, the recording, take the 80% passing quiz. To find that quiz on our YouTube channel, head to the YouTube link logo. Click below it to click show more for the description, and then on the right there you'll see a link to a Dropbox quiz as well. And again, just a huge thanks to our board of directors, volunteers, all of our sponsors, Panasonic Ventilation, T-Stud, Mitsubishi Electric, Build Equinox, among many others who support our work and allow us to keep doing what we do. And Ty, let me know if you need me to kick it back to you for any other slides you want to show off, and I have them here too. But this is a really great question, and I think a lot of questions are kind of coming in. The kind of broad question is, how are ventilation system manufacturers, be it ERV, HRV, smart ventilation, you name it, how are they going to be adapting to this kind of new reality here? And so specifically to that question here is, are there ways to set for zero recirculation during an outbreak, assuming that that's something that you want to do, to be able to have it be only full filtration, and whether there's going to be N95 equivalent filters available for ventilation systems, And how can they be safely disinfected?
Yeah, several good questions in that. See if I can hit them. But I think, say, with conventional HRVs, ERVs, which normally are not designed for recirculation, that in that case, you need to then consider how to add recirculation or filtration, which could either be done with local, say, air filtration, as you might buy from a big box store, or in some manner if you have a central furnace air conditioning system, to keep that in circulation so many hours a day. Typically that airflow rate, where we run around 200 CFM as a normal airflow with our ventilation system, and for a 2,000 square foot home, that turns it over within about an hour to 90 minutes. In homes that become, well, with central systems where you're running maybe 1,500 or 2,000 CFM, you don't need to run it that often in order to turn the house over and to regularly filter, but you do need to run it. And the swing seasons are times when often your air conditioner or central furnace will be off and you're not getting any circulation. And definitely MERV 11 or greater to help get viral particles as well as get small particles in general out. For disinfecting, there was a great webinar a week ago that was a free webinar by ASHRAE, and I think you can find the links to that webinar as well as a PDF by Professor William Bonfleth, who studies indoor air quality. He's one of the foremost researchers in environmental quality in buildings. But if you look up William Bonfleth and ultraviolet sanitation, you'll find some very good information on ultraviolet light and infectious agents. And so it's a very current topic. And these are some things we've been conducting research on, and you'll hear some announcements from us coming up in the near future on that as far as our serve ventilation system. But you really need to think about, in the home, recirculation is actually a good thing just because it keeps the house more fully mixed so that one room, like a bedroom, doesn't get highly concentrated in infectious agents, as well as just CO2 and then the VOCs that the human, as part of our regular metabolism, emit. That's also not that healthy for us to rebreathe. So recirculation in a home, in a low density environment, has benefits for trying to keep the house uniformly fresh, as well as then bringing in fresh air to keep that bulk freshness under control. As a house gets more complicated, and to us, greater than 3,000 square feet or so, but depending on the room and the architectural design, then zone dampering and distributed sensors also help so that there may only be 1 or 2 occupants in, say, this 10,000 square foot home, but you're able to see where the pollutants are being generated and then to more directly zone fresh air into that space as well as exhaust more directly from that region. And you can find more out about that on our website, so I won't go into more detail on that. But so good filters. Ultraviolet is a good means, but you have to watch the materials that are exposed to ultraviolet as well as your own health. But there's some good options on that. And then within the home environment, especially recirculation, we feel is very important in all homes for particulate management.
What can you tell us about, I mean, the role of humidity in this at all? I mean, you kind of briefly touched on it, but is it important to control that? Are these smart systems able to control that or detect humidity levels as well?
Yeah, so we monitor humidity. We don't actively manage it, although we have the capability to. And in some homes, we either do that directly or indirectly through through using our sensors for then activating an inline humidifier or dehumidifier. And as I mentioned, the Mitsubishi projects that we have coming up, in which the Serve-2 and a Mitsubishi ducted mini split are integrated together with the Serve controlling both. That gives us the additional capacity for, say, whole house dehumidification through the Mitsubishi's capacity, but using the Serve as the primary sensor and controlling system for that. Now, humidity as far as viral infections, it's very weird. There's some viruses that, like the rhinovirus, one of the cold virus families, that seems to do well in high humidities, say greater than 50, 60% humidity, while others, like the respiratory viruses, tend to become less efficient in being, tend to be less efficient and less viable at higher humidities. They're more efficient at low humidities. And so you may have seen some of these graphics that show this kind of sweet spot of, say, 40 to 60% humidity where viral activity is lower. It's not eliminated, but the respiratory viruses, the winter viruses, tend to be less efficiently transferred at that humidity. And the viruses at the, say, summer viruses or year-round viruses that may seem to do better at higher humidities are less active. Within high performance homes, as we're most often connected to, although we're in many, many conventional homes, we find that wintertime humidity in northern climates, that these well-sealed homes with, say, passive house level sealing, 0.6 air changes per hour, 50 Pascal type sealing, that they will naturally have an indoor humidity of about 40 to 50% in the winter with smart ventilation, because you're only bringing in air as you need it. When it's windy out and you're infiltrating that much more air into your house, even in a highly sealed home, or the number of door openings, if you've got young kids or pets or things that you're regularly opening and closing the door, all of those are adding air, and a smart ventilator senses that and then brings in that additional amount that you need. That ends up in winter type systems keeping the humidity at a much more comfortable rate than a fixed ventilation level does. And so we haven't found the need typically to actively control humidity. And in more southern locations, for sure, dehumidification is needed. And in summer conditions in more northern climates, humidification, because everything you do in the house, breathing, cooking, showering, humans are humidifiers and our activities add humidity. So all of those things add into that need for some level of dehumidification. And our 4-part report series on humidity management that's located on our website should provide a lot of guidance to people on the characteristics of managing humidity, as well as the machines that are needed and the energy needed in different climates to manage humidity.
How far off are we from our smart systems maybe being able to potentially detect viruses?
Within, say, a regular house or building environment, I'm not sure. You can hardly turn around these days without a new capability. Within the last 10 years, this capability to have in situ real-time genetic monitoring of a local biome, it's just amazing, where more than 10 years ago, you had to put culture plates out or collect samples that then you would culture over a period of time. And now, as people can track down hundreds and hundreds and thousands of genetic tracers of bacteria and viruses and molds and other genetic markers, are just finding that it's a much, much more vibrant biome than we ever knew really existed. So while it seems like it's sophisticated technology, the way medical instruments and biometrics are getting put into watches and cell phones and other things, maybe it's going to happen within 10 years. And similarly, like this University of Maryland social distancing parameter, I think this is going to feed in, say in our own case in smart ventilation, we discuss a concept called preventilation. We feel very strongly that this day and age of big data and artificial intelligence used in a beneficial manner, as anything can be used as a weapon or as a tool, that this is going to help us live healthier, both collectively and individually, by perhaps tracking infectious agents as well as pollutants and pollens and allergens and asthma triggers, but also, say, social distancing may be an indicator as far as bouts of depression or migraine headaches or stress-induced factors, coupled with the air quality and other things that an individual is doing. I don't know where it's going to lead, but I mean, we've got this big soup of new technologies, and that's part of the fun we're having, is sorting through those to see how to best make use of them, but in a simplified manner. We don't want this controlling anyone's life. We want this in the background so you can go on thinking and living and doing the things you enjoy while having the peace of mind that your local environment is being effectively managed.
Well, Ty, thank you so much for joining us. We are at our time here. But just real quick, where can people go to find more information, learn more about, either what we're talking about here or just in general about Build Equinox?
Yeah, our Build Equinox website, buildequinox.com, has a lot of our reports and reference materials, as well as 4 papers that you can download from the literature, like Professor Milton's papers on ventilation and sick days. And so there's more than enough. If you have any insomnia, in addition to my monotone voice dragging on for over an hour here, there's many reports there that help knock you out at night.
Great. And just so you all know, hopefully within the next couple months, we'll be joining Ty through a personal tour of his own house and everything he did. So look out for that. We're real excited to hopefully have you back on then.
Yeah, looking forward to that.
Yeah, we'll be excited. And a public service announcement before we close off. We have to ask everyone to, make sure you stay indoors, shelter in place if you're not an essential worker or taking care of a loved one or feeding your family. Please stay in to help stop this thing. When you do go out, make sure to check the CDC guidelines on the appropriate masks to wear. Put those on, keep others protected. And I think we can beat this thing, and hopefully we'll all see you all at a conference here soon together. So take care, everyone. Have a great rest of your week. Stay safe. Thank you.
Thank you, Brent.